Hi, my name is Valentina Betancourt, and this is my presentation for Lab 4, Circuits and Capacitors. First, an introduction to the lab. The purpose of this lab was to predict the behavior of circuits containing resistors in series as well as in parallel, and in the experiment we used multimeters to measure the actual values of conventional current and potential difference in the circuits, and then used this to examine the behavior of ohmic resistors and capacitors. Physical principles. First, we're going to discuss energy conservation, as well as current conservation, and relevant formulas that will be seen are Kirchhoff's loop rule and Ohm's law. Expected results for the lab. First, I predicted the currents I1 and I2, that would be measured by the two ammeters. I stated that I was equal to I1, which was equal to I2, and we can find I such that I was equal to V over R. Plugging in 1.5 V times 2 since we have two batteries, and dividing that by 147, we get 0.0204 amps. Then the question asked to reverse the connection of one of the two ammeters, and what does the ammeter read when it was inserted backwards? I stated that there was no change. Step 1 was to model the results. When I created my model, I changed the voltage on the batteries as well as the resistance on the resistors to match our given problem. My predicted current, I, was equal to 0.02 amps, so that was approximately equal to the mathematical computation that I previously stated, which was 0.0204 amps. Step 2 was replacing the ammeter with a voltmeter. Upon replacing one ammeter with a voltmeter, the ammeter read 0 volts due to the fact that we now have an open circuit. Still, the voltmeter still read 3 volts, and this is due to the drop in voltage of 3 volts. Step 3 was to remove the voltmeter from the circuit and close the circuit with a wire. I used the voltmeter to measure the potential difference for each part of the path around the circuit. Parts B, C, D, E, F, G, G, H, and H, A all read 0 volts, and part A, the connection AB read negative 3 volts, CD was 0.93 volts, and EF was 2.07 volts. Still, the sum of the delta V's was equal to 0. Step 3 had some questions about the lab. It asked, when I attached the voltmeter, I altered the circuit. Why doesn't the ammeter reading change? I stated the ammeter reading is not dependent on the voltmeter, but rather other factors that did not change, such as the resistors. For this reason, the ammeter reading didn't actually change. I then connected the voltmeter across the resistor again and noted the ammeter reading. Once again, I stated there was no change and it still read 0.02 amps. I then replaced the voltmeter with an ammeter in parallel with the resistor. It asked what happened through the current through the other ammeter and why. I stated that since the current takes the path of least resistance, it now reads 0.07 amps. Part 3 also asked to calculate the resistance of each of the following. Here I have my R of the ammeter was 0 ohms, R of the resistor was 46.6 ohms, R of the R100 resistor was 103.5 ohms, and the R of the wire was 0 ohms. Part 4 dealt with an RC circuit. Here the settings was a battery with 9 volts, a light bulb with 10 ohms, and a capacitor with 0.2 F. And the observations here was that the light bulb started out very bright, but it progressively dimmed until it was completely off. And I said that we expected similar results if we disconnect the battery and only connect the light bulb directly to the capacitor. More questions based on part 4. When I removed the battery from the circuit, the capacitor began discharging. What happened to the current in the circuit? I stated that the current went back to normal until the capacitor was completely discharged. When I first connected the battery to the capacitor was charging. What happened to the current in the circuit? I said the current decreases as the capacitor charges. And then asked to measure the time it took in seconds for the capacitor to charge using this bulb, and it took approximately 9 seconds to charge. And then the time that it took to discharge was approximately 11 seconds. Now with the second bulb, it took about twice the time, so it took 18 seconds to charge, but 21 seconds to discharge. Here I just have a graph of my measured times versus the ln, the natural log of delta V over delta V naught. And lastly, more concluding questions on the lab. What if you were doing this lab in real life and used an actual ammeter instead of an ideal simulated ammeter, and what's the difference in these two situations? I said that the ammeter should account for some internal resistance instead of reading 0, so this would alter the values that I got previously. And if I was doing the lab in real life and used a real battery to charge a real capacitor with no resistor in the circuit, how quickly would our ideal model predict the capacitor to reach full charge? And would this happen in real life? I said in real life we would experience more resistance, and our ideal model would predict the capacitor to reach full charge much faster than it actually would in real life. So the model was much quicker than it should be in real life if we were actually carrying out this experiment. That concludes my lab. Thank you.